This lesson is going to be a situation where we take things that we've already learned about curves in general, and we now apply them to a particular application of curves, that is their ability to describe motion in space. So what we're primarily going to do here is we're going to talk again about parametric curves, position as a function of a parameter t, but we're now going to explicitly think of t in terms of time. And so if t is time, then position as a function of t now represents a trajectory in space. We call this object, this line in space. When it represents the path of an object, we call it a trajectory. And so the derivatives of this vector function, r prime of t, now take on objects with physical meaning. So r prime of t, the rate of change of position with respect to time, is now clearly the velocity, and we can go ahead and call that a vector v of t equal to r prime of t. And the second derivative of position with respect to time, just like we saw in Calculus 1, is now called the acceleration. We can call that, give it its own name, we can call that vector a of t. But what we're going to do now, the reason that we went to all the trouble of defining these intrinsic properties of curves before turning right around at the end and going back to parameterized curves, is that we're now going to be able to talk about these everyday physical objects, velocity and acceleration, in terms of these properties intrinsic to curves that we've learned about through some harder effort earlier on. And we're going to learn a couple of interesting things. So let's go ahead and do our first result. So velocity, r prime of t, we're sort of abandoning the idea of reparametrizing curves in terms of their own arc length, but suppose we could. Suppose we knew that the arc length function, s of t, and r as a function of its own arc length. If we wanted to then calculate the derivative with respect to time, we could use this information and take the chain rule. So dr dt could become dr ds dt. This is just the chain rule. But we've seen both of these objects before when we were talking about intrinsic properties of curves. So this ds dt is the magnitude of r prime of t, and dr ds we saw was the unit tangent, t hat. So this says that velocity can be written as the magnitude of r prime times the direction of r prime. And so in this way of writing it, we see a couple of facts. We see that velocity is always in the direction of the unit tangent. That's not an entirely surprising fact, but it allows us to write down velocity in terms of this intrinsic property of the curve. So velocity always goes in the direction of the unit tangent, and its magnitude is always given by the derivative of the arc length function, which we can interpret as the speed. So this object, ds dt, magnitude of r prime of t, we can always think of when we're talking about trajectories as the speed. And because there's not really a good letter, we're going to reuse the letter v without a vector sign to represent this scalar object of the speed. It no longer has a direction. Velocity vector has a direction. The speed v is just a scalar. And again, that's unfortunate, but s is already taken, v is already taken, and so on. So we're going to reuse v, but without the vector sign. So that doesn't seem all that interesting, but things get more interesting when we look at acceleration. So here we have acceleration. It's r double prime of t, which is the time derivative of r prime of t. Now we already saw that r prime of t up here was equal to, I'll just change the order of these, ds dt dr ds. I did that for no particular reason than that these things end up being in the order that is given in the book. So we take the time derivative of this product. We have to use our product rule. We get the second derivative of s with respect to t times t hat plus the derivative of t hat with respect to s. The derivative of t hat with respect to t. We saw that in order to take derivatives with respect to t, we can take a derivative with respect to s and then multiply by ds dt using the chain rule again. So this becomes dt ds times ds dt is the derivative of this, times ds dt again, left over from the product rule, and so we get dt ds times ds dt squared. However, every one of these objects can be rewritten. So what is the second derivative of s with respect to t? that is the first derivative with respect to t of ds dt, which we're calling the speed v. So we rewrite this as v prime of t times t hat. ds dt squared, that becomes v squared. And we already saw that dt ds in the previous lesson was the curvature kappa times the unit normal. So we get here an expression for the acceleration that is in terms of the unit tangent and the unit normal, these properties intrinsic to the curve. And this is interesting. This has some very interesting interpretations that, in fact, you're already familiar with. You already know this formula. You just don't know that you know it. So what we see is that acceleration has two components, a tangential component proportional to the rate of change of speed, and a normal component, which is proportional to the rate of change of direction through this kappa term. It's also proportional to the velocity squared, but assuming a fixed velocity, then this normal component is proportional to the rate of change of direction. And everyone who has ever driven a car already knows this, whether you realize it or not. So if you are pulling away from a stoplight in a straight line, then your curvature is 0, so this term contributes nothing. And we focus instead on this term here. You're going in a straight line, you're accelerating away from the stoplight, and so your speed is increasing. And that means that you feel a force in the direction you're traveling as the car pushes you along. Your seat pushes you forward to accelerate you in that direction, and so you feel that force pushing you in the tangential direction. On the other hand, if you are coming up to a corner or you're out driving on some windy, deserted road and perhaps driving a little faster than you ought to be driving, which I don't recommend, not condoning that at all, but perhaps you've done it, then if you are turning a corner at constant speed, you will feel a force in the normal direction proportional to the curvature that you are turning. So if you turn to the left sharply, then you will feel yourself flying to the right, which seems not what this thing is saying, but eventually you will hit something on the right side of you, and that object will then accelerate you to the left in the direction that you're turning. And so this term is of the correct sign. The car, as it accelerates around the corner, will cause you to accelerate around the corner as well, and so in some capacity or another, it will push you to the direction that you're turning. And so one thing people don't realize is that in order to turn corners, even if you're going the same speed, you have to accelerate. You have to exert a force and acceleration to change direction. And this formula for the acceleration nicely encapsulates that. Again, it's not anything new. We already know what acceleration is. It's the second derivative with respect to of position with respect to time. But the work that we previously did on curves allows us to express that in some nice intuitive way. So following up on this car analogy, let's do an example. And I'm going to have to mess with my screen here a minute. The question is, how does a race car turn a corner? So let's think about it. I see that the answer is already on the screen, and you see that too, but let's think about this. A race car is trying to travel through a circle. Let's assume that the car goes through the corner in a perfect circle. That circle will have a curvature of 1 over its radius. What is the goal of a race car going through a circle? You might think that the goal is to get through the corner as fast as possible, right? That's what a race car does. A race car wants to go as fast as possible. And so you might think that its goal is to go as fast as possible through the corner. That is not actually true. Typically, the goal of a race car is to exit a corner with maximum possible speed. If you have a big long straightaway coming up, then you want to exit that corner as fast as you can so that you can carry that high speed with you all the way down the straightaway and accelerate. So if two cars come through the corner, if one car goes very slightly faster through the corner but ends up with a lower speed, then the car who took a little bit longer to go through the corner but exits with a higher speed will rapidly out-accelerate that car because it had a head start on its velocity. So let's say that our goal is to exit a corner with maximum speed. And what's a realistic constraint on the race car driver? The constraint is that if you go too fast, you will skid out and crash into the wall. And so what's really happening is that tires only have a certain amount of grip, and that's basically a friction force that they can withstand before they start slipping. So let's assume that the tires can only withstand in the normal direction a certain maximum acceleration g for grip. So if we go back up to our equation, we say the tires can only deal with a maximum force in the normal direction with magnitude g, and so that means that kappa v squared has to equal g. Okay, so the consequence of this constraint is that kappa v squared equals g, and so the velocity which is associated with that amount of grip is equal to the square root of g over k, g over kappa, and if kappa is 1 over r, then that's the square root of g times r. So it's the square root of the grip of the tires times the radius of the circle. And the consequence is that if you have a larger radius, then you can go faster, which gives you a faster exit. So the goal of a race car driver should be to turn the corner with maximum possible radius. So let's draw some pictures. Here we have a corner. We have a right corner, and the race car driver is going to go this way and then turn the corner to the left and proceed down in this direction. And so let's investigate a couple of ways that the race car driver could turn the corner. Here's one way. The race car driver could come in on the inside and then make a tight change in the corner and then exit the corner on the inside lane, leaving the corner. So this spends very little time in the corner, just this tiny little distance here. However, that is 1/4 of a rather small circle, and so the driver will spend rather high curvature on that, and as a consequence, small radius means small velocity. Okay, so that means the race car driver, in order to take this path, will have to slow down very considerably and will exit the corner very slowly. Here is another possible trajectory that the race car driver could take. You see that we come in on the outside and we turn the corner through the outside and then leave on the outside. And you'll see that this has very much larger radius, and so the race car driver will be able to leave very much faster. So this is a superior way to go through the corner because larger radius means larger exit velocity. Even though the path through the corner is larger and will take slightly longer, the driver will have a larger exit velocity. Now, if you know anything about racing, which you probably learned through playing video games, you may know that there is yet a better way to traverse the corner. And it basically starts here. If you said, boy, it's too bad that this road is so narrow, which makes me only possible to take this radius of circle. If only the road were wider, I could make a very large radius circle like this and use that to traverse the corner, and then I'd be going really fast when I left the corner. So if only that were able to fit inside the racetrack. And you may or may not be surprised, again, depending on whether you've played a lot of racing games or not. But in fact, this trajectory does fit inside the racetrack. As long as you don't go through the corner, wait until you get to the corner to start turning the corner. So here we have a situation where we begin turning the corner much before we get to the corner. We start on the outside. As we go through the corner, we come down to the inside, and then we go back to the outside. So you may have known this already, that the fastest way to traverse a corner is to start on the outside, come to the inside, and end up on the outside. The reason for that is it allows you to take the largest possible circle radius or the smallest possible curvature through the corner, and that allows you to maintain the highest possible velocity. Who knew that intrinsic properties of curves could be so interesting, right? So that's enough of that. We will now talk a little bit about integrating, right? So the velocity and acceleration from the position function are derivatives, but we can also work backwards. And this will be the first instance in which we've really done much integrating of vector functions that has a lot of physical meaning. We all saw in Calculus 1 and maybe introductory physics that we have Newton's law giving force equals mass times acceleration. What you may not have done before is to put vector signs on that. More correctly, force and acceleration are both vectors. So if we do it more correctly, we have the force vector equals mass times the acceleration vector, or acceleration equals force divided by mass. Now, if you're given the acceleration, hopefully we saw in Calculus 1, that as long as you're also given an initial position, r0, and an initial velocity v0, then it is possible to integrate once to get the velocity from the acceleration, and integrate again to get the position from the velocity. So if we're given the forces acting on an object, then in principle, we can integrate that acceleration function to get the velocity and do it again to get the position. And this is a natural application of integration. We'll do just one kind of long example, also sort of fun, to illustrate this concept. And that is to calculate the trajectory of a cannonball. Or perhaps cannonballs are getting sort of outdated as a source of example material, so this could be an artillery shell, or something less warlike. It could be a baseball. But whatever it is, we can calculate its trajectory. So suppose we have an initial position at the origin. We'll just go ahead and call the place which we start at the origin, and so we'll call that 0, 0. That's fine. And suppose we launch it with a given velocity, a given speed, v0, and a given direction, and a given elevation, theta. So we're pointing up some angle theta, and the direction vector associated with that angle theta is x. The I component is cosine theta, and the j component is sine theta. So our initial velocity is v0 cosine theta, comma, sine theta. And we'll just work in 2D here. And then we know that the acceleration is pointing in the negative j direction and has magnitude g. And here on Earth, g equals 9.8 meters per second squared. But for math, we don't need the number, we'll just use the letter g. We now integrate. The velocity is the initial velocity, given here, plus the integral of the acceleration from 0 to t over some dummy variable tau. And so this, I should have said earlier, this illustrates why we need the initial condition, because when t equals 0, this integral gives us nothing, and so the constant needs to be equal to the initial velocity. And then this gives us the velocity at any future time later than the initial time. So we integrate negative gj from 0 to t, and we get negative gtj. So that velocity is v0 cosine theta I plus v0 sine theta minus gtj. And we integrate again to get position. We have the initial position 0, 0 plus the integral of squiggly line means all of this. And when we integrate both of these things with respect to t and evaluate at 0 and t, we get v0 cosine theta t plus v0 sine theta t minus 1/2 gt squared in the j direction. So you may know this already, but here's how you can show it. What is the shape of this trajectory? What can we say about it? Well, one thing we can notice right away is that this is, again, an idealized situation, no air resistance or anything like that, so it's a very unlikely cannonball shot in a vacuum. But the x velocity is always the same. It moves linearly in the x direction with constant x velocity. Only the y velocity is affected by gravity. So we start with our initial y component moving up, and then as time evolves, we slow down and turn around and come back to Earth. We can calculate the shape by eliminating the parameter t. So from here, we have that x equals v0 cosine t, or t is x over v0 cosine theta. And if we plug that value of t into the equation for y here, then we get y equals tangent theta x minus g over 2 v0 squared cosine squared theta x squared. Now these are all just constants, so what this is a parabola that starts at 0 and goes off, and it has a negative concavity. So this is just simply a parabola. Most of us knew that. A more interesting question is, what is the optimum firing angle to achieve the maximum distance? And many of you know this as well, the correct answer. But again, here's where it comes from. How do we find it? Well, we say, first we need to answer the question, how far is it going to go as a function of theta? And to figure out how far it's going to go, we need to find out when it hits the ground, recall from Calculus 1. So we need to take the equation for y and set it equal to 0, and that'll tell us when it's at the ground. It has two solutions, t equals 0, obviously, that's the time when it was fired, and it has a second solution, 2v0 over g sine theta. So we'll take that second value for t, plug it into the equation for x, right here, and we get the landing position, which can be written as a constant times sine 2 theta. Then we just need to maximize x as a function of theta, and we need then, to make that happen, that cosine of 2 theta equals 0, and that of course occurs at pi over 4, because cosine pi over 2 is 0. So pi over 4 is of course 45 degrees, and this is why you shoot things at a 45-degree angle if you want to maximize the distance. Now, this is not actually true, like many things that you learn in basic math and physics classes, because air resistance is involved. And so you will note that Tiger Woods does not use his 7-iron to achieve maximum possible distance. And that's because when you factor in air resistance, things change a little bit and you end up needing to take a shallower angle if you are firing your object at a very high speed, for which air resistance is going to be important. But at low speeds, this is still a good approximation. So if you're just playing baseball, for instance, you can't throw a ball that fast compared to the speed of a golf ball. And so baseball players throw things, outfielders, for instance, throw things more like a 45-degree angle than do golfers. You could extrapolate this to all kinds of other sports, but I will let you do that in your spare time.